Hello students, in previous video we have seen m-ary tree. Now here let's see few properties of m-ary tree. What is the m-ary tree basically? M-ary tree is such a tree, if a root is there then the root has that many children, the same number of children to all the parents in that tree. That is known as what? A m-ary tree. For example, this is now 3-ary tree. This is 3-ary tree. Look at this, root has 3 children, while this vertex has again 3 children. This one again has 3 children. So this is what? M-ary tree or 3-ary tree basically. So now let's see few properties of this m-ary tree. Properties of m-ary tree. The first property of it says that the first property, a full m-ary tree with I internal vertices, has n equal to m into I plus 1 vertices. Now, how can we say this? Let's see the proof of it. If or in a m-ary tree, each of internal vertex means what? A parent. Those vertices which are the parent are nothing but what? The internal vertices. So in this m-ary tree, each of the I internal vertices has how many children? Each parent has, if it will be m-ary tree, then it has m children. Vertices has m children. So if each has m children, then the number of vertices, total number of vertices are what? M into I plus 1 will be what? The root of it. Hence, m children. Hence, we can say there are m into I vertices. M into I vertices. But the root is not a child of any vertex. Therefore, total number of vertices is what? M into I plus 1, and that is nothing but, that is, we can say n equal to m into I plus 1. This is the proof of this first property. Now let's see the second property. Now the second property, a full m-ary tree with first n vertices has I equal to n minus 1 upon m internal vertices, and L equal to m minus 1 into n plus 1 upon m leaves. These many internal vertices and these many leaves. Second, I internal vertices has n equal to m into I plus 1 vertices and L equal to m minus 1 times I plus 1 leaves. Then next one, L leaves has n equal to m minus L minus 1 upon m minus 1 vertices and I equal to L minus 1 upon m minus 1 internal vertices. Internal vertices means what here? If n is known, we can determine I and L, right? If I is known, a value of m should be known, right? So if I is known, we can determine n and L again, and if L is known, then also we can determine n and I. The relations between these one with each other are given to us in this property. So now let's prove this. Let me prove first one. Suppose the first one, suppose a m-ary tree has n vertices, therefore as we have seen from previous property, therefore by property I can say, therefore by property 1, n equal to what? M into I plus 1. If I is what? I is nothing but what? Internal vertices. I are the internal vertices. Then this one. No, then from this we can easily write I equal to what? N minus 1 upon m. This one we have to prove in the first one for about I. Now let's see for L. Also every vertex is either a leaf or an internal vertex. These are the two choices for them. Internal vertex, right? So n equal to, we can say, therefore total number of vertices are n. Therefore n is what? Sum of leaf and internal vertex. So L plus what? I. Now let me put the value of I here. So this will give us, therefore from this I will get L equal to n minus I. That is same as n minus 1 upon m. This is what I from this result, right? So simplify it, we will get, this is what? Mn minus n plus 1 upon m, right? Take n common from here, we will get m minus 1 into n plus 1 upon what? M. This is what? L. This is again what? Result. If n is known, m is known, then we can easily determine I and what? L from it. Now let's see the second part. Let's do the second part. In second part, what? M is known and I is known to us, right? So now this is already we have seen in first property. N equal to m into I plus 1. This is by property 1, I can say. By property 1. This is a proof of second one, okay? Property 1. Fine. Now the question is left for L. Now you know L is what? N minus I. Right? So N is how much? This one. M into I plus 1 minus I. So now take these two terms together, we get m minus 1 times I plus what? 1. This is the required result here, right? Now let's see the next one, third. The proof of third one. What the third says? L is known now, right? So as n is what? L plus I, and n is what? M into I plus 1 also. So put let it be 1. Okay, put n equal to L plus I in n equal to m into I plus 1. Let me put it here. Okay, therefore what we get? We get L plus I is nothing but m into I plus 1. That gives us m minus 1 into I is equal to what? L minus 1. If we shuffle the terms, so I we get L minus 1 upon what? M minus 1. This one we have found, right? Now the question is left for n. So for that, now n is what? N is I plus L. So let's put the value of I here. So I is what? L minus 1 upon M minus 1 plus L. So this will be what? This is ML, or let me write L minus 1 plus ML minus L upon M minus 1. So here it will be a mistake. Here it will be what? ML minus 1 upon M minus 1 is this. This L and L get cancelled. This is nothing but what? ML minus 1. Positive term I have written for negative latter. So upon M minus 1. So N is what? ML minus 1 upon M minus 1. This is the proof of it. Proof of this. Complete proof of this second property. Now let's go for the third property. Now the third property I won't prove, because you can, if you want, you can prove it by method of induction. Let me give that property to you. The third property, there are almost m raised to h leaves. M raised to h leaves in a m-ary tree. In a m-ary tree of height h. If m-ary tree of height h, then almost it has m raised to h leaves. You can prove it by induction. I will give it as a homework to you. Now this is about the properties of m-ary tree. Now next part we have to see tree traversal. Now what it is? Ordered rooted trees are often used to store information. If you look in a medical store, when we want some of the medicine, that time they were exactly choose that box in which that the same medicine was kept, right? So there will be some sequence. So that part is what in that type such a trees are used. Tree traversal, or the way or the algorithm is there. The order rooted tree are often used in store information. We need procedures for visiting such a vertex of an order rooted tree to access data. In this section, we will see several algorithms for visiting all vertices of an order rooted tree. This order rooted tree can also be used to represent various types of expressions such as arithmetic expression involving numbers, variables and operations. The different listing of vertices of order rooted tree used to represent expressions are useful in the evaluation of these expressions also. Now we have to see the traversal algorithm. Now there are various algorithms, but among these we have to see 3 in our syllabus. We have to study 3 in our syllabus. Procedures for systematically visiting every vertex. What the definition of it? Procedures for systematically visiting every vertex of an ordered rooted tree. Every vertex of an ordered rooted tree are called traversal algorithm. Traversal algorithms. Now here we have to see 3 such algorithms. We will study 3 such algorithms. Now which are these 3 algorithms? The first one is preorder traversal. Then second one we have to study in order traversal, and the third one post order traversal. Okay, now let's see the definitions of each one: pre-order, in order and post order. Now let me give these things in detail to you. First, pre-order traversal. Pre-order traversal. Now what it is? Let T be an ordered rooted tree. Ordered rooted tree with root R. If T consists only of R, then R is the preorder traversal of T. Otherwise, suppose that T1, T2 and so on up to suppose Tn are the subtrees at R. From left to right in T. From left to right in T. The preorder traversal begins by visiting R. It continues by traversing T1 in preorder, then T2 in preorder, and so on until Tn is traversed in preorder. Now the same definition, this is nothing but what? The definition of it, right? The definition of this one. Now this definition diagrammatically I can written as, if this is a root, then here step 1 we have to go for what? Visit R first. visit R, this root, right? Then step 1 is this. Then suppose it has one subtree T1, or let it be T1, another subtree suppose T2, and so on and so on. Tn subtrees are there. Then in step 2, visit T1 in preorder. In step 3, visit T2 in preorder. And this step n+1 is for what? Visit Tn in preorder. Let me take an example so that this will be clear to you. First of all, we have to visit root, then this subtree, then next subtree, then next subtree. As such we have to go. Let's see the example for it so that it will be clear to you. Example. In which order does a preorder traversal, visit the vertices in the rooted tree. The rooted tree is given as, this is A, B, C, D, E, F, G, then D, H and I. This is a rooted tree given to us. Now we have to follow a preorder traversal here. So solution for this. First of all, we will visit what? A root. So we visit root vertex A, and then its subtrees from left to right in preorder. So if this is, then look at, first of all we will visit A, right? Then we will visit B, fine. Then we will visit C with its subtree. So C with its subtree E, here F and what? G. Then D with its subtree H and what? I. Now again we will consider this is our another tree. So now this subtree we are considering as our examples. So here we will visit C first, then E, F and G, then visit D first, then H, I as such. So further, how does it? Here A, then B as it is, then we will get C first, then we will visit E, then we will visit F, then G, then D, then H and then what? I. Right? This is the final answer. This is the way for visiting these vertices with preorder traversal here. Now let me give one example of this kind as a homework to you. Fine. Suppose one example as a homework. This is A. It has a child B, another child C, suppose here D, here F, then again E is here, suppose J, here I, M, N, and then what? O. Here C has a child G, then H, and here K, L. Now if you feel it will be difficult, don't worry. Look at, first of all you will visit A. Final answer, let's discuss the final answer. First of all we will visit A, right? Then this whole subtree, right? This whole subtree we will visit. Again this whole subtree. So in this subtree again we will take what? B first. B. Fine. B will be taken. Then D. D. Then what? This E with this subtree. E and what? F. E and F. But E with subtree, so let's go with that. Again I. Then I with that subtree, then M and O are there, right? Then I with that subtree, then M, N, and then O. Later on we will go for J. Then we will go for F. In between that these will come. Obviously while taking B, it has a D, this subtree and F, right? But this subtree gives us this much, right? In this order we will visit them. Then we will come to this again. Then after F we will go for C. Here this B subtree is over. Now C. C. Then what? Further G. Right? Then H. And H has a subtree. So K and what? L. This is the way for visiting the vertices. This is final answer you get. Fine. This is a pre-order traversal. Okay. Here we will stop for this video. In next video we will see in-order traversal and post-order traversal. Also some examples. Thank you.